Dan is the James McGill Professor of Psychology, Music, and Computer Science at McGill University and a founding member of CIRMMT. The CIRMMT Student Executive Committee chose the keynote speakers for today's symposium by process of discussion and voting, with the aim of selecting speakers with a broad appeal across CIRMMT's research axes. Dan's comprehensive background in numerous aspects of music production and music research make him an excellent match for today's event. He will be presenting some of the great experimental work recently conducted by students. So please welcome Tanna Levitin.
Thank you all for inviting me here. I'm going to talk about some interdisciplinary work that we did in my laboratory, several CIRMMT students of mine and I. But before that, I thought I'd talk a little bit about interdisciplinarity. The kind of work that I do is by necessity interdisciplinary. In music cognition, we have to draw on sources such as music, obviously. Perhaps less obviously, it's important for us to work with colleagues in medicine, genetics, computer science, information science, and neuroscience in order to better understand the phenomena that we're studying. And I think that the whole idea of interdisciplinarity is increasingly important. CIRMMT was founded 12 years ago with the idea that some of the most difficult problems facing those of us interested in the science of music and musical communication couldn't be solved with any single discipline. Wisław Wojcik, the founding director of CIRMMT, is here, and I'd like to acknowledge his great vision and all the great efforts he made 12 years ago to bring us all together. So one of the questions is why interdisciplinarity is important and why it's increasingly important today. Well, the growth of knowledge over the last few decades, as you know, has been extraordinary. The sum total of information that has been generated in the last 10 years alone is equal to all the information in history leading up to that period. So in other words, all the information generated, if you were to calculate it and express it in exobytes, up to the year 2000 is the same as the information generated between 2000 and 2010. So with that explosion of information has come specialization, of course. If you had gotten a college degree in the time of Isaac Newton, if you had studied for 4 years and gotten the equivalent of a bachelor's degree in biology, you would pretty much know, actually I'll expand that. If you had gotten a bachelor's degree in science, in Newton's time, you would pretty much know almost everything there was to be known about science. I mean, you wouldn't have been as creative or intelligent necessarily as Newton, but you would have learned all the facts about the world that he knew and that were known to any scholar. You certainly would have known all of the biology that was known if you took a bachelor's degree 400 years ago or even 200 years ago. Now, if you take a bachelor's degree or even a PhD in biology, you can't even know all there is to know about the visual system of the squid. That's how much there is to be known. And so what this suggests is that working by ourselves with what we can learn on our own, we can't tackle any of the big problems. And the big problems really require not just knowledge from within one's domain, but knowledge across domains. So, for example, some of the big inventions of the last several decades came from interdisciplinary collaborations. As you may have read about in Jonah Lehrer's new book, Imagine, the invention of Velcro was not the product of somebody who was studying the properties of physics or material science. It was an outsider to the field who happened to notice that when he took his dog for a walk in the field, burrs would get stuck in the dog's tail, and they were very hard to remove. And he thought, what an interesting property this is. Maybe there's a commercial application for it. Similarly, the inventor of Scotch tape had no training in adhesives. The inventor of Scotch tape was somebody who worked in the sandpaper industry. And his job was to try, what sandpaper is a bunch of gritty stuff, sand or something like it, that's been stuck to a paper backing. And the problem with sandpaper in the early part of the 1900s was that the gritty stuff kept falling off the backing. The adhesives weren't adequate. And so there was this person working who knew a lot about the properties of abrasives, trying to get the abrasive material to stick to the backing. And he discovered a particularly bad adhesive which kept coming up and not adhering. And he thought, well, there might be a use for this. It could be a removable tape. Scotch tape is what came out of that. Somebody not working in the field, not a specialist in chemistry or adhesives. And of course, to all of us, the invention of FM synthesis is one of the great examples of modern-day interdisciplinarity. John Chowning was a composer, not an electrical engineer at all, who happened upon this phenomenon of sound modulation while he was experimenting with an early synthesizer at the artificial intelligence laboratories at Stanford in the 1960s. So here was a guy who was an early embracer of interdisciplinary research, a composer working in an artificial intelligence laboratory who stumbles upon something, quickly tries to find an engineer who can explain it to him, and out of that came FM synthesis, the entire Yamaha line of DX synthesizers, and the second most lucrative patent in all of Stanford University history. It brought in $25 million. And that was second only to the birth control pill, for which Stanford also holds the patent. So just a little pep talk about why we're all here. We're all here to engage with one another and learn from one another's different backgrounds. And the research that I want to talk about today really came from this kind of interdisciplinary interaction. As you saw in the first talk today, Frédéric Chiasson is a saxophone player who's, as I understand it, whose work required collaboration with a composer, an engineer, and a psychoacoustician. And then later you'll hear from Mahtab, a systems and design engineer who collaborated with Bevan, a composer, in the lab of a computer science and acoustician, Marcelo Wanderley. So the idea of this fertility and this cross-talk is very, very important. That is what we brought, my students and I, to the research I'm going to describe today. We began with a simple question: what separates a good musical performance from one that's not so good? We asked people initially just to give us free responses in this kind of open-ended question. And people said things like, well, a good performance, it moved me. It was emotional, expressive, artistic, sincere, soothing, inspiring, energizing, aesthetically beautiful. And my students and I should mention, this is primarily the work of Anjali Bhattara. This was included in her doctoral thesis, and Anna Tiravolis, who did this as a special project, and Marie Duan, who worked on it as an undergraduate honors thesis. They did most of the work. In talking about all these adjectives that you see here, all these ways of describing a good musical performance and distinguishing it from one that's not so good, we note that what's happening in the acoustic domain, not the emotional or mental domain, is artists can primarily change these four parameters. They can manipulate pitch or intonation, they can manipulate the rhythm or the phrasing, the dynamics of the performance, and the timbre. And that's pretty much what they have to work with as acoustic parameters. To borrow from Kendall and Carteret, the idea is that the composer has some emotional qualities in mind that he or she wants to convey through the performance. And these are typically written down in some musical notation that the performer interprets, and the performer adds his or her own ideas about emotional expression to the written score, and then tries to communicate some kind of mixture of the composer's emotions and the performer's emotions to a listener, who in turn will have his or her own emotions that will intersect with what was intended, hopefully, by the other two. And the idea of Kendall and Carteret's figure is that there's sort of this circle of communication going on, and there's this Venn diagram where there's this perhaps very tiny little area where everybody is experiencing the same thing, but there's, as you see, these enormous areas of individual interpretation and variation. So what we have is a case where there's some intended expression on the part of the composer and the performer, and then there's perceived expression in terms of the listener. As Roger Shepard says, this is a problem of mental representations. The composer and the performer have a certain mental representation, the listener has a certain mental representation, and what we as cognitive psychologists want to study is the relationship between those. It's, in another sense, thinking of it statistically, this is a classical psychophysical case of how changes in the physical world are mapped and represented in the psychological world. Now, the 4 parameters that I mentioned earlier, the 4 degrees of freedom as they apply to the piano can't really create variations in intonation, but for a piano, you have when the key is hit, how hard the key is hit, which translates to the velocity or loudness, when the key is released, and then pedaling. Out of that comes all of the expressivity of the piano. We chose to study piano performance because it provided a more constrained and limited case rather than studying vocal performance or wind instrument performance where, pitch intonation is a parameter, and the other reason that we decided to study emotional expression in piano performances was the invention of the Yamaha Disklavier gave us a kind of perfect laboratory device or tool for studying emotional expressivity. People play the Yamaha Disklavier, there are sensors underneath all 88 keys that record the performance and turn it into MIDI format, and we can then study how it is that a pianist actually played in terms of these 4 parameters, and a lot of the hard work of encoding the performance is taken care of. So ideally, we'd like to extend this work to saxophone and to voice and to percussion instruments and a number of, all instruments, string, violins. But in this initial study, and I emphasize, this is, no experiment can solve all the problems that you want to solve or answer all the questions you'd want to answer. This is just one experiment that gets at a limited set of issues in a very large landscape. So there are these 4 parameters of expressivity on the piano. Only these 4. Of course, this is a nonlinear dynamical system, meaning that there are complex interactions between the parameters. But what it comes down to is that all of that beautiful emotional nuance you hear in a piano performance, whether it's by Brendel or Oscar Peterson, all of it comes down to these 4 decisions that the pianist can make and the interactions between them. Because of that specificity and that limitation, we thought that this would be a good launching point to study expressivity in performance. Now, note that those of you that are MIDI programmers or MIDI users, you'll note that each of these has a correspondence in MIDI. That is, the computer keeps track of each of these values. So when a key is hit is MIDI note onset, how hard it is hit is MIDI velocity, when the key is released is MIDI release, and pedaling is the MIDI pedal position. In the talk today, I'm going to talk about timing, amplitude, and pedaling. So the MIDI note onset and the MIDI release are collectively, in this scheme anyway, I'm going to think of as timing. Now, I mentioned that this was a classical psychophysical problem. In general, when we talk about psychophysics, there are some changes in the physical world along some dimension that we try to map to changes in the psychological world along that same dimension. The changes could be level in the light of a room, or loudness of a noise, or weights that you're holding in a knapsack. How much weight do I put in before you notice that the weight of the knapsack has changed? It might be in the intensity of smells, the saltiness of a drink or a food. In general, what we're interested in is the shape of the psychometric function that relates the physical to the psychological. That's the psychological psychometric curve or the psychophysical function. And that's what we're going to try to build here for emotional expression. Now, variability in timing and amplitude, I'd like to ignore pedaling for the moment, are widely regarded as what makes music sound expressive rather than dull or lifeless. In the tradition of Western music, in fact, expressive performance is largely based on systematic variation of duration and intensity. So just as actors and orators rarely read a text in a monotone or isochronously with a steady, equal number of seconds per syllable. Expert musicians rarely perform a score strictly as written. The score is not all the information that's necessary. It's rather a starting point for individual interpretation. More so as you proceed to the modern times from Bach, right? So as you get into the Romantic composers, there's more variation expected, more deviation from the score is expected. So performers are introducing subtle and not so subtle variations in timing and amplitude. So we first systematically stripped away all of the variability from an expressive performance to conduct our experiment. We set the amplitude and timing values to the mean that we obtained from an expressive performance, and then we created intermediate versions of the performance by adding the variability back in. This resulted in a continuum of versions that vary in their level of expressivity. We covaried timing and amplitude in the first manipulation we did, as they normally would be in an actual performance, and in a few minutes I'll talk about how we separated those. So the way that we conducted the experiment was we got Tom Plant several years ago. He was the head of the piano performance division here at the Schulich School. We had him come in and play some pieces on our Disklavier, as he would normally play them in a concert. The Disklavier recorded his performance with all those sensors that are underneath the keys and underneath the pedal. I should mention that the Disklavier resolution is limited to MIDI, so there's 127 bits, but the resolution is deemed high enough that Yamaha Disklaviers are often used in international piano competitions and in auditions. So contenders in these auditions or in these contests will often just send in a CD or a disc with their performance, and it'll be played back on the Yamaha Disklavier for the judges. This is one way that judges can evaluate the performance without having any identifying information about the player and without being influenced by the flourishes that the player makes or whether the player is attractive or unattractive. It's a way to keep that part neutral. And again, the point is that the quality is deemed not perfect, but good enough for most purposes. So Professor Plant came in and he played these performances. We had the computer record of what he did, and then we stripped away all of the variability in his performance. So we set each note to the mean value for amplitude across his entire performance, and then we normalized the length of the notes. So although he played some notes longer and some notes shorter, we set all quarter notes to be exactly the same length, and all eighth notes were exactly half as long, and all half notes were exactly twice as long, and so on. So here is a sound example of what Tom Plant actually played as reproduced by the Disklavier. He played 30 seconds of each of 4 different pieces, all of them Chopin nocturnes, 2 in a major key, 2 in a minor key. We limited it to 30 seconds because the experiment is going to require that listeners listen to many, many different versions in random order, and if we played the whole piece, the experiment would be too long, listeners' attention would fade, and we wouldn't have good data. So this is the version after which we normalized or just stripped away all of the expressive variation. Again, played back through the same Disklavier. Sounds kind of like a kid practicing, doesn't it? Because kids are practicing without emotion and expression most of the time. They're taught to keep regular time. Now, I told you that having taken the expressive version and created this mechanical version, we then systematically added back the expressivity by using interpolation. So there's this variability in the amplitude and variability in the timing in the expressive version, and we can add back, say, 50% or 20% or 80% of that variability to create intermediate versions. Here, for example, is the 50% expressive version, where half of the timing variability and half of the loudness amplitude variability has been added back in. Oops. So we had created a bunch of different versions. In this particular experiment, there was the mechanical and the expressive, and then 25%, 50%, and 75% versions. And we mixed all these up across the 4 different nocturnes and across the different versions, and we played them to people in random order. And they simply had to answer on a scale of 1 to 10, how expressive do you find this music to be? We asked the question in several different ways. We asked, how emotional do you find it? How much emotion do you think the performer is feeling? How much expression do you think the performer is conveying? It turns out it doesn't matter the way we ask the question. The wording of the question doesn't create significant differences in the ratings. And really the question was, would people be able to hear the difference? And if so, would they be able to recapture what's in effect a rank ordering? Would they be sensitive enough to the differences that they would rate the 100% version as more emotional than the 75% version, and so on? And what would the shape of their response curve look like? Would it be linear? Would it be logarithmic? As we were putting the experiment together, one concern we had is that a subject might answer the question without thinking about musical expressivity at all, or without thinking about emotion. They might simply discern the amount of variability present in the different versions. In other words, the way experiment 1 was designed, the versions with the most variability are the ones that we conceived a priori as having the greatest expressivity. So expressivity here is confounded with the amount of variance in the performance. So we needed a control condition, and for that we created a random musical condition where all of the variability that was in the expressive version is still present, but it's present in random places. So all of the amplitude values for the notes were randomly distributed among the notes, and all of the duration values were randomly distributed. So the random version has all of the variability, it just doesn't cohere in any musically sensible way, but it does serve as a control for that. And here's what it sounds like. Kind of sounds like poor Tom is drunk, doesn't it? So these graphs here show the left hand and right hand, that didn't come out very well, did it? These are showing the amplitude curves for the 5 different versions, the expressive 75, 50, 25% mechanical, left hand versus right hand, and then the random version. And this shows the same thing. I'm sorry, this is the timing variation. This is the amplitude variation. So you can see that flat line is the mechanical version, and you can see that as we move from expressive to mechanical, we're reducing the variation. So for experiment 1, 16 participants, both musicians and non-musicians, heard each sound file in random order 3 times, and they answered this question. And as I said earlier, it doesn't matter how you ask the question, you get the same data. There were 4 Chopin nocturnes, as I said. We covaried the timing, amplitude, and pedaling. Participants were just unselected for musical ability. We took whoever walked through the door. And hypothetically, you might expect that this group of people can't hear the differences, and if you were to graph hypothetical results where their rating is normalized to a 0 to 1 scale, they might say, well, they're all the same. Alternatively, you might get some kind of a linear curve where they rate the expressive as most expressive on down to the mechanical version as least expressive. Or another alternative hypothesis is that you'd get something like a sigmoidal or ogive-shaped curve. This is common in a number of biological and psychological phenomena where you see this, what an engineer would call a threshold function, where at the ends of the distribution, it's more difficult to distinguish what's going on, and most of the sensitivity is in the middle of the distribution. So we had these three hypotheses about what the data might look like, and these are what the data actually look like. So we did, in fact, get this sigmoid. The difference between the 75% and the 100% versions were statistically indistinguishable, as were the 0 and 25% conditions, but these three were statistically distinguishable. What this means is that when you cross over, after a certain point, when you're at 75% expressive, although trained musicians and certainly pianists would hear the difference, the average person statistically didn't hear the difference. And notice here's that random one, which was rated as the least expressive. If you look carefully, you'll see also that the halfway mark between the lowest and the highest ratings is not at the 50% level. It's at about 58%. So in other words, people need to hear about 58%, 60% expressivity to hear it as 50%. So you might have had the same experience yourself. When you heard the 50% version, it might have sounded a little less than halfway because you need a little bit more than half in order for it to sound that way. This is a property that we've seen over and over again with these kinds of experiments. This is a scatter plot showing the sensitivity to our manipulation. So what we're regressing here is years of musical experience by their sensitivity. And it turns out that the more musical experience you have, the more sensitive you are to the manipulation. That is, the steeper the curve you get. So if we were to plot this curve separately for expert musicians versus non-musicians, you'd have a steeper function for the musicians, a shallower function for the non-musicians. So what we concluded here was that participants were able to distinguish these different levels of expressivity, and the participants were able to recover the rank orderings of the versions, even in a random presentation. I should emphasize the participants had no idea what we had done. We didn't explain the manipulation to them. We didn't tell them anything about our hypothesis. We just threw at them all these different sound files. And I think it's actually quite extraordinary that in an acoustic sense, there's a rank ordering. You know, some of them are, objectively speaking, more expressive than others. And without knowing anything about the experiment and just making these 1 to 10 ratings, our 16 participants recovered or regenerated that same rank ordering. And so doing this, we were able to construct a psychophysical expressivity curve. I also want to say that as we were just starting this experiment and talking to people about it, everybody said this would be impossible. They said, you can't quantify musical expressivity, you can't quantify musical emotion, it's not subject to this kind of measurement. And we were inspired by something that Galileo said, which was measure what is measurable, and that which is not render measurable. Actually, he said it in Latin, but that's the English translation. So we thought not to be daunted by the fact that this seemed unmeasurable. We strived to do as Galileo had advised, to render it measurable, and we were really pleased that it worked out. But that wasn't the end of it. We thought we should independently vary the timing and amplitude to pursue the question of which is more important in conveying expressivity. So here, for example, we're holding the amplitude constant and varying only the timing. Or holding the timing constant and varying only the amplitude. And here's the 50% point for each. Fixed amplitude, varied timing. Fixed timing, varied amplitude. As you can probably hear, especially if you're a pianist, in all these experiments, in the stimulus preparation, the pedal is following the percentage manipulation. So in the expressive version, the pedal is allowed to do what it was doing. In the mechanical version, there's no pedal. In the 50% expressive version, the pedal travels 50% of the range that it traveled in the expressive version, and so on. So when we gave people these, this was the honors thesis for Marie Douan, who's now in medical school. We have now a pair of psychophysical curves, one for the varied timing and one for the varied amplitude. And what we see here by the steepness of the curve is that the greater difference in expressivity is carried more by timing than by amplitude when the other is held constant. And you can look at the effect size to quantify the influence of one versus the other. The varied timing had an eta squared of 0.32, and the varied amplitude had an eta squared of 0.11. So varied timing accounts for 3 times as much of the variance in emotional expressivity as does varied amplitude. In experiment 3, this was actually an accident, to be honest. We took the first 2 studies and we submitted them to a journal, and we were rejected. And one of the reviewers, Bruno Repp from Haskins Labs, who always signs his reviews so that you know who to be mad at, said that he thought that we hadn't really done all that we should have. We should have asked the question, what happens if instead of interpolating between 0 and 100%, you extrapolate between 100% and some larger number of the expressivity? What happens when you add more expressivity than the pianist actually used? In other words, when Tom Plant came in our lab and played, that was just one performance on a particular day. To call that 100% or optimal seems somewhat disingenuous. It's just what he did. What if he had put in 10% more expressivity that particular day? What would it have sounded like, and would people have preferred that? So, in fact, we extrapolated and created 2 more versions at 125 and 150%, and we asked people to rate those. Here's 100%. And 125. And 150. He sounds a little drunk again, doesn't he? So, oops. So this is the curve that we get when we present the 100, 125, and 150, along with all the other versions. So it turns out that although 100% wasn't rated the highest, 125% wasn't statistically different. So in the actual raw data, this number was slightly higher, but not in a statistically significant sense. And then it really drops off for the 150% version. People considered that to be not as expressive. So the 100% version was, in effect, some kind of optimal, or somewhere near there. So the ideal level of dynamic and temporal variation in piano performance may certainly differ depending on the piece and on the player, but overall, increased variability beyond a certain point yields diminishing returns. It just sounds overdone. For our last experiment, we tested individuals with autism on the covariate timing and amplitude stimuli. Why would we do such a thing? Well, by definition, individuals with autism suffer impaired emotional understanding. This has presented the research field with a paradox over the last 20 years. If music is the language of emotion, primarily an emotional form of communication, why is it that so many people with autism learn to play an instrument or are attracted to music? So hypothesis one was that music is an island of spared emotional communication in autism. Hypothesis two was that individuals with autism are attracted to some other aspect of music, not its emotion. Apart from its emotional content, they might be attracted to, say, its orderliness or its structure, the same way they like to go to hardware stores and look at the orderly arrangement of products on the shelves, and the way they like to line up their toys. So the experiment can help us to choose between these alternative hypotheses. The subjects were 30 adolescents, typically developing, and 30 adolescents with autism recruited from McGill's autism clinic. Again, this is the interdisciplinarity. We worked with the Faculty of Medicine, Department of Psychiatry, to test, recruit, and evaluate these patients. So this blue line is the data I showed you earlier from our regular control subjects in the expressivity experiment. And I'm going to add in now the graph in orange for the autistic individuals. So they were unable to tell the difference between the different versions. They were not sensitive to the ordinary and customary cues that the rest of us are when listening to music. Now, it doesn't mean that they don't experience emotion in music, but it does mean that they're not paying attention to the same things that we are and responding to those same things. Here are the random points, by the way. Both groups rated them as different. Now, we had this funny little anomaly in one group of control subjects where the random was rated higher than the mechanical version, and we can't explain that. That's going to require some further research. So what we conclude from this is, at the very least, as I said, individuals with autism are not sensitive to the same expressive cues used by the rest of us, and it strongly suggests they're not perceiving the emotional and expressive variation in these pieces the way normal controls are. So what we've learned about the psychophysics of expressive piano performance as an initial step towards understanding expressive performance in general is that average listeners are able to detect subtle variations in timing and amplitude, and musicians are more sensitive to these expressive cues. The results are similar, regardless of whether participants are asked to rate expressivity or emotionality or a number of other similar questions. The variation in timing is more salient than the variation in amplitude in the overall perception of expressivity. And that expressivity curve, the psychophysical function, appears to be nonlinear with a threshold function at the ends. And finally, what we like to think is that we've introduced a method for studying emotion in music that we hope will be adopted and used by others. This is something that can be easily used with MIDI instruments and with a little bit of signal processing with non-MIDI instruments. So most of the credit goes to the students. Anjali Bhattara, this was her doctoral dissertation. She's now a postdoc in France. Anna Teravolis is currently a doctoral student in the Faculty of Education in the school psychology program. And then other members of the lab all helped out. Thank you very much.